We started section 2.6 on Friday, and we covered page 1, right, on combining functions, right, adding 2 functions, subtracting 2 functions, multiplying 2 functions, and dividing 2 functions. And then we reviewed function composition, right, taking the composition of 2 functions. And remember that open circle between f and g, rather just spells the word fog, right? That's not a multiplication symbol. That's called a composite operator. And that says we're taking the composite of the function f with the function g as a function of x. And by definition, that is equal to f of g of x. And so we demonstrated function composition with this exercise right down at the bottom of page 2. And I said this is where exam 2 would end, right, with page 2. So what we're doing on pages 3, top of page 3, right, will not be on the exam. The exercise at the bottom of page 3 and one at the top of page 4 have to deal with composition of functions, so indirectly, right, they're on the exam. So before we do the exercise at the top of page 3, let's do the exercise at the bottom of page 3 and top of page 4, since it involves taking the composition of 2 functions, okay? Then we'll pick up right where we left off on Friday. So in this exercise, we're taking the composition of function f with the function g as a function of x, and we have f of g of x. Okay. And so let's just remind ourselves f of x is equal to 3 over x minus 2, and g of x is equal to x squared minus 5x, okay? So the first step is replace g of x with what it's equal to, and it's equal to x squared minus 5x. So this is equal to f of x squared minus 5x. And now I evaluate the function f at x squared minus 5x, right? So wherever I see an x on the right-hand side of f of x, I replace it with x squared minus 5x. So this is equal to 3 over x squared minus 5x minus 2. Now we got to simplify, okay? So to simplify this difference, we need a common denominator, right? And the common denominator is x squared minus 5x. So this is equal to 3 over x squared minus 5x minus, and then, you know, 2 can be written as 2 over 1, if you want to express it that way. And then you multiply the top by x squared minus 5x, and the bottom by x squared minus 5x. Now, a lot of college students have an aversion to using parentheses. And when you don't use parentheses, okay, you often, when you got to distribute a minus sign, you don't distribute the minus sign correctly, okay? You only change the sign of the first term, not the second term, and it totally messes up the problem. Okay? So now we have a common denominator, right? 1 times x squared minus 5x is just x squared minus 5x, okay? And so we got common denominator, so now we can combine the numerators over the common denominator. So we have 3 minus 2 times x squared minus 5x over x squared minus 5x. Okay. Well, now you got to distribute the -2 inside the parentheses. This is why you put stuff in parentheses. Because if you don't, you'll write this as -2x squared minus 5x, and it messes up the entire problem. Okay. So we distribute the -2 inside the parentheses, and we have 3 minus 2x squared plus 10x, all over the common denominator, x squared minus 5x. Okay. Now, if you want to, you can write the numerator in descending powers of x, right? Minus 2x squared plus 10x plus 3. Okay. But the numerator doesn't factor. The denominator you can factor out an x. But the numerator doesn't factor, so you can stop right there. Okay.
So when you distribute, you only do the number that's closest to the parentheses, not all of the numbers?
Yeah, because this is, you're subtracting 2 times that from the number 3.
Oh, okay.
Right? This is like, instead of what's in parentheses, if I had 3 minus 2 times 7, okay, you would multiply, right? By PEMDAS, you would multiply 2 times 7 first, right? And get 2 times 7 is 14, and 3 minus 14 is negative 11. Okay. So it's only the 2 that's being multiplied by x squared minus 5x. Okay. All right. Any other questions? Okay. So top of page 4, we have find and completely simplify. The composite of f with g is a function of x. Let's state the domain in interval notation. Okay. So we have the composite of f with g as a function of x, which is equal to f of g of x. And where f of x is equal to 3 over x minus 2, and g of x is equal to x squared minus 5x. So first step, replace g of x with what it's equal to, and it's equal to x squared.
Are we doing one with that?
Oh, did I write down the wrong thing?
F of x and g and x are different.
Yeah. I'm using an old set of notes. Sorry, ladies and gentlemen. I'm using an old set of notes. Thank you for straightening me out on that. Okay. Yeah, so f of x, we have f of x is equal to 3 over x squared minus 1. Got it up on the big screen, and I still got it wrong. And g of x is equal to x plus 1, right? Yeah, I started putting up the problem we just solved again on the, yeah. All right, senior moment. Okay. All right, so we have f of x equals x squared minus 1, and g of x equals x plus 1. So we got to find the composition of f with g as a function of x, and then state the domain in interval notation. Okay. So g of x is x plus 1. gotta evaluate f of x plus 1 by putting in x plus 1 in for x, right, on the right hand side of f of x. So f of x plus 1 is equal to 3. Now, instead of squaring x, we're squaring x plus 1. So x plus 1 has to be put in parentheses, right, because you're squaring that binomial. And then minus 1. All right. Now, when you get really good at FOILing, right, you can do the FOILing without writing it out. But just to remind, x plus 1 squared is equal to x plus 1 times x plus 1. And so when you multiply first terms, you get x squared. When you multiply outer terms, you get x. When you multiply inner terms, you get x. When you multiply last terms, you get plus 1. And so this is equal to x squared plus 2x plus 1. So in the denominator, we have x squared plus 2x plus 1 minus 1, right? Don't forget this minus 1 out here. 1 minus 1 is 0. So we're left with 3 over x squared plus 2x. So that's the composition of the function f with g as a function of x. Okay. Now the domain. How do we find the domain? This could be exam 2 question, right? How do we find the domain?
Denominator not equal to 0.
Yeah, right? Because if the denominator equals 0, you got 3 divided by 0. 3 divided by 0 is undefined, right? So the denominator, so this function is undefined if the denominator equals 0. Okay, you can't have that. So to find the domain, we set the denominator x squared plus 2x not equal to 0, right? X squared plus 2x can equal any other number, it just can't equal 0. And now you know you can factor out an x on the left. So we have x times x plus 2 can't equal 0. So we have a product of 2 factors. So either the first factor can't equal 0, or the second. And the second factor can't equal 0. The second equation, when you solve for x, you get x can't equal -2. So the domain is all real numbers except for 0 and -2, right? And so in interval notation, our domain is -infinity to -2, union -2 to 0, union 0 to infinity. That's all real numbers. Except -2 and 0. Right? The domain is all real numbers except for -2 and 0. Okay. Any questions on that, ladies and gentlemen? Okay. All right, so now let's go back to the top of page 3. And you can take the composition of more than 2 functions. So top of page 3, we're taking the composition of 3 functions. So we have f of x is equal to the square root of x minus 3. G of x is equal to 3x minus 5, and h of x is equal to x squared minus x. So f of x is a transformation on the square root function. G of x is a linear function, right? That's mx plus b form on the right hand side. And h of x is a quadratic function, right? Its graph is a parabola. So the composition of f with g with h, remember these open circles are composite operators, is equal to f of g of h of x. F of g of h of x, right? So like when they were taking composite two functions, you start with the middle one and you work out, right? So we're going to replace h of x with what it's equal to. H of x is equal to x squared minus x. Now remember, we're dealing with inbreaded parentheses, right? Yeah, I have the same number of left-hand parentheses as right-hand parentheses. So now we have to evaluate g of x squared minus x. So define g of x squared minus x. Wherever we see an x on the right-hand side of g of x, we replace it with x squared minus x. So we have f. Now you got to be really careful here. We're going to take x squared minus x and put it in for x over here, right? And so we're going to have 3 times x squared minus x minus 5. Okay. We have 2 left-hand parentheses, 2 right-hand parentheses. Okay. These 2 outer ones, right, go with the function f, and then this one goes with g of x squared minus x. So now we can distribute the 3 inside. Okay. Now if you wanted to, instead of doing the math inside parentheses here, down here on the side, you could have done g of x squared minus x is equal to 3 times x squared minus x minus 5, right? And then once you simplify this, replace this up here. So when we distribute the 3, we have 3x squared minus 3x minus 5. What's f of 3x squared minus 3x minus 5? Put that in for x and f of x, right? And so f of all this is equal to the square root of 3x squared minus 3x minus 5, okay? And then don't forget the minus 3. And now when you simplify under the radical, you have 3x squared minus 3x minus 8. So the composite of the function f with the function g with the function h as a function of x, right, is equal to, I left off the x over here, guys. Composition of function f of the function g with function h as a function of x is equal to f of g of h of x, which is equal to the square root of 3x squared minus 3x times 8. Okay. So you can take the composition of a dozen functions. Okay. All right, you're not limited to 2. It comes in 3 functions, 4 functions, 5 functions, 6 functions, 7 functions. So, okay. Any questions on that? Okay. The last topic is on decomposition. Okay. We know how to take the composite of 2 functions. Now we're going to take one big function and rewrite it as the composite of 2 functions. Okay. Taking the composite of 2 functions is pretty straightforward, right? You know how to find f of g of x. Okay. But decomposing a big function into 2 smaller ones is, students sometimes have difficulty with that because there's no magic formula. Okay. So we're going to take big F of x, which is equal to x plus 2 squared. Take squared or cubed? Minus the absolute value of x plus 2. Okay. And we're going to write it as a composition of 2 functions, f and g. Okay. So we're going to write f of x as the composition of the functions f and g as a function of x. So whatever we set f of x and g of x equal to, when we take the composition of those 2 functions, we got to get big F of x. Okay? So we're going in reverse. That's why it's called decomposition. Okay? So g of x is called the inner function because it's inside f of x. And f of x is called the outer function because it contains g of x. Okay. Well, the first thing you want to do is find the inner function. In this case, g of x. Okay. So you got to set g of x equal to something. Okay. Well, you notice that inside big F of x, we have a function of x, x plus 2. Okay. So you got to look for a function of x, right, inside the big function. Okay. And you can see we have the function x plus 2 inside big F of x. So we set g of x equal to x plus 2. Because f of x, you could say, is a function of x plus 2. Okay. And so that is our inner function. Now to get the outer function, f of x, okay, you replace x plus 2 with x. Okay? So to get the outer function, f of x, little f of x, you replace x plus 2 in big F of x with x. Okay. So if I replace x plus 2 with x, I have x cubed. And when I replace x plus 2 with x, I have minus the absolute value of x. A known formula for finding the inner and the outer function. You have to recognize what the inner function is, right? What the function of x is inside of big F of x, okay? And then you set g of x equal to that. And then you replace that inner function with just x. And then that, what's left over, right, is your outer function, little f of x, okay? Now, how do we know we've decomposed this correctly? We do a check, right? So big F of x is the composite of f with g is a function of x. It's equal to f of g of x. So how do you evaluate f of g of x? Well, first you replace g of x with what it's equal to. It's equal to x plus 2. And now how do you evaluate f of x plus 2? You replace x, or where you see an x on the right hand side, you replace it with x plus 2. So when I replace this x with x plus 2, I have x plus 2 cubed. And I have minus the absolute value of x plus 2. And that checks, right? Because that's equal to big F of x, what we were given. Okay. So whatever you choose for f of x and g of x, when you take the composition of those two functions, you have to end up with the big function, big F of x. Okay. Or you have it decomposed correctly. Miss, did you have your hand up? What was it, you? It's the name of this function. I mean, we can use capital letters, we can use little letters, right? So, and I could have used little h, right? So this is the name of the function. And so, big F is different from little f, okay? So big F of x and little f of x are two different functions, okay? It's not intended to confuse you, right? We could have used little h here and said little h of x is equal to the composite of little f and little g, right? Remember, we just use letters of the alphabet to name our functions. And there's a difference between the function big F and little f. Okay? There's a big difference between big G and little g, big H and little h. Okay? Yeah. Okay. All right, any questions, ladies and gentlemen? Nada? Okay. All right, so that wraps up section 2.6, right? So you've got everything you need to successfully complete the WebAssign homework. And so we really don't have enough time to get started on 2.8. So we'll do that on Wednesday, or Thursday, I guess, okay? So have a good day, you guys, and I'll see you on Wednesday, and I'll get the exam reviews posted on